So good afternoon, AP Stats kids. It's Wednesday and it's April 1st. I live in rural Maine and we had snow last night, which is not atypical, I guess, but depending upon where you are in the country around the world, maybe you didn't have snow. We like to call it a dusting of snow, which is just a little bit on your car, I guess, and it's already melted. But winter is still hanging around up here in rural Maine, and where the days are getting longer, and that's a good thing. Um, so my good friend Luke yesterday introduced what we call Unit 9. And I'm going to summarize that as what we would call inference for regression. So we want to come up with confidence intervals, and we want to do hypothesis tests on what we call the slope of the least squares regression line. And depending upon how your teacher sequenced things earlier in the year, when I say least squares regression line, or I'm actually going to try and clarify that, the sample least squares regression line versus the population least squares regression line. Your teacher may have opted not to teach that earlier in the year, and many teachers kind of combine that unit in what Luke and I are doing the rest of this week. So if this is brand new to you, don't worry about it. I'll try and make the connection between what perhaps some students learned earlier in the year with what we call the sample least squares regression line versus today the population least squares regression line. Luke and I have, starting next Monday, a plan for the next month. So April 6th through May 1st, we have full weeks. And all of those sessions will be dedicated to reviewing for this year's 2020 modified AP Stats exam. So all of what we've done the last 4 or 5, 6 lectures and the rest of this week will be on units 8 and 9. Again, that's none of chi-square or inference for regression will be on this year's test. But we wanted to make sure that you guys had the full AP Stats experience. So when you go off to college next year, and your professor may have assumed that you know this, and so that was our logic. But we start reviewing starting next Monday. We're going to publish a schedule of all of our daily topics for really the next month. That's probably going to come out later this week or early next week. And on Friday, the College Board is going to announce publicly some more details on this year's exam. So stay tuned. Luke and I will make sure that you guys are 100% up to speed on what's in this year's test, what isn't, how long is it, how many questions, pretty much anything we can share publicly. We're going to go ahead and share with you guys. So I'm just going to segue to my PowerPoint, and there's our daily slide. That's going to be the first slide. It's a cool kind of normal curve, right, with maybe a histogram or something below it. So you've seen that before, and you've seen both Luke and I, hopefully at this point. Maybe not, maybe you're brand new today. If so, welcome. So again, my name's Brendan Murphy, and I teach at John Baptist Memorial High School in Bangor, Maine. It's a really interesting school. I won't go into great detail, but it's a great school, great kids, and I'm a lucky guy. I have a great job. My good friend Luke, he teaches at East Kentwood High School in Michigan, and he's great. I've known him for years. We're both what we call AP readers. So we've graded thousands and thousands of AP Stats exams over the years. And both he and I are also what we call consultants. So in the summer, we run professional development from teachers. And I've learned so much from all the wonderful teachers that have taken my workshops. And perhaps I had one of your teachers over the years. So this was last night's homework. So if you didn't sit in on Luke's session yesterday, he introduced and pretty much set the stage for what we call inference for regression. So let me just give you a couple, 20 seconds, 30 seconds to just read the problem. I'm going to read through it again. And this is when we say modified, this wasn't the full free response. We're going to do just part A today. So let me give you 20 seconds or so to read the problem, and then I'll walk through the homework, and then we'll get into some new stuff. Okay, so let's look at this problem. Again, this was from the 2006 AP Stats exam. This was question 2. I was a reader that year, and I actually think I was one of the 150 readers or so that graded this problem. It sort of rings a bell. So a manufacturer of dish detergent believes that the height of soap suds in the dish pan depends upon the amount of detergent used. So I call that setting the stage. There's no mathematics there, but it's just trying to sort of contextually give us an idea for what's going on. A study of the suds height for a new dish detergent was conducted. So I hear the word study, and I don't know if that's an experimental design or really what that is, but I'm just again, just setting the stage. 7 pans of water were prepared. My first gut says, boy, that's a really small sample size. I would love for that to be 27, 57, 100, 5,000. As a general statement, larger sample size is always better, but it is what it is, and I guess 7 is better than nothing. And all the pans were of the same size and type and contain the same amount of water. So we're trying to keep our variables consistent. That sort of makes sense. The temperature of the water was the same for each pan. Again, we're just setting the stage. An amount of dish detergent was assigned at random to each pan, and that amount of detergent was added to the pan. So there's my randomness. I want to look for that in almost every problem. That's sort of a good thing. And it feels like perhaps we put different amounts of detergent in the pan. Then the water in the dish pan was agitated for a set amount of time, and the height of the resulting suds was measured. So that's a lot. You may have to go back and read that a couple, 2 or 3 times. That's perfectly fine. I like to tell my students, really understand the problem before you dive in and do any mathematics. Like understand what they're asking you to do. A plot of the data and the computer output from fitting a least squares regression line, so LSRL, that's what we abbreviate that as, least squares regression line, to the data is shown below. Okay, so there's the scatter plot, and it looks like my explanatory variable is amount of detergent. My response variable is the height of the suds, SUDS. And it sort of feels logical to me that if I put more detergent in and shake it up or pour more water on it, the suds are probably going to get a little higher. And so we probably all experience that. And so before I do any mathematics, I want to just basically try and understand the problem, see if it makes any sense. And so down below here, you'll see we call this a generic computer output here. I'm going to switch over to my document camera. We're going to be looking at the same problem here. Okay, so here's the same problem. So I call this a generic computer output. The reason we say generic is we're not trying to do some marketing for any of the software companies. There's many different software packages out there. Most of them are excellent. So hopefully you've had an opportunity to use that in the classroom. And I did watch a little bit of Luke's video yesterday, and he was excellent as always. And I think he did talk about how do we read a generic computer output. So there's a lot of numbers here, and there's a lot of statistics here. And as a general statement, we don't need all of them to answer any problem. And what we want to do is be able to find the information that we're specifically looking for. There's times when you're going to see something that isn't part of the curriculum, and R squared adjusted, that's not part of our curriculum. So sometimes I just cross that out, and I don't want it to get in the way. But there's lots of numbers here, and don't be overwhelmed by that. So the homework last night was to write the equation of the fitted regression line. I guess that would be the same thing as the least squares regression line. I use the two sort of interchangeably, I guess. Define any variables used in this equation. So I'm going to show you 2 different ways to write the least squares regression line or the fitted regression line. Different books present it different ways, and both get full credit on the AP exam. If that line wasn't here, in other words, if it didn't say define any variables, we would still want you to define the variables. So anytime you write a regression line, please define the variables, whether that line is there or not. So I like to say to my students, well, if I look at constant and coefficient, so that negative 2.679, that feels like my y-intercept, or my initial starting value for my equation for my sample least squares regression line. So constant coefficient. You'll see we're going to do lots of generic computer outputs today. That number is sort of always in the same spot. And so I think that's my A value up here, my initial starting value, my y-intercept. The amount, or the number that goes with the amount here, I think that's going to be my slope here, or my rate of change. And so we do want you to be able to find those two values relatively quickly from a generic computer output. And so if you're with me the other day, I think you realize that I write really, really poorly. I'm a lefty. I have the curse of being a lefty. And so my first equation here, y hat equals negative 2.679 plus 9.5x. That's in this form here, what we call y hat equals a plus bx. What I haven't done right now is identify the variables. So this answer right here is not complete. We would want you to identify the variables. And so over here on the right, I just said X is the amount of dish detergent in grams that we added, and Y hat is the predicted mean height of the suds, or the predicted height of the suds. So I need both of those if I choose not to identify my variables. That's the way my textbook presents it. There's nothing wrong with that. That would be full credit on the AP exam. You have the correct least squares regression line, and you've identified the variables. Others of you, your teachers or your textbooks, may have you write it, I guess, sort of in words. And so here you can see I have height of suds, and I have this huge hat over it. And you can see I didn't do a very good job of drawing in my hat there. Equals negative 2.679 plus 9.5 detergent, or detergent in grams, or something like that. And so here I don't really need to identify the variables because I physically have written those in my least squares regression line. So again, both of these would be considered acceptable on this year, on any AP exam. This one here is just another way to do it. And again, your teacher, your book may have a specific way of doing it, and I'd follow the book, but please know that both of those are acceptable. So that's a quick review of the homework. And again, this concept here of coming up with the least squares regression line, my sample line based upon my 7 data points. And I'm going to build upon that today to come up with what we would call the, or what I call the population least squares regression line. If you've never seen that before, or you say, I don't think I've ever done a scatter plot, bivariate data, least squares regression line, don't worry about it. Luke and I are going to cover that in our review. So there was a part B and C to this problem, as you can see, and I think I may come back to this problem on Friday, what we're calling a FRQ Friday. So on Friday, I'm going to do nothing but a couple of 2 or 3, 4 free response questions, and really dive into the rubrics and how we score and grade these things and what we're looking for, keeping in mind that this year's modified AP Stats exam is going to be nothing but free response questions. Okay, so I'm back to the PowerPoint, and so let's take a look at perhaps what's going to be new with this lesson. So again, y hat equals a plus bx. That formula is on the formula sheet that you'll have for this year's exam. We say y hat equals a plus bx, and that's going to be the least squares regression line for my small sample of data. The equation below it is what I would call the true least squares regression line. Some books call it the population regression line. And you can see that in the top equation, I'll call that my sample. Those are English letters that make sense. And in the bottom equation, you'll see some Greek letters, and I'm going to switch back to my document camera and try and make a tie-in for you guys. Okay, So the first day of my AP Stats class every year, we get to count M&Ms, and so that's pretty fun. I buy a bunch of different bags of M&Ms. And on the first day of AP Stats, I really want to start to differentiate for my students what we call a sample statistic, SS, and what we call population parameters, PP. And I think Luke did something very similar yesterday. So X bar is the sample mean, and you probably worked with that earlier this year. We're going to use the sample mean to make a prediction or forecast, an estimate for what we call mu, the population mean. P hat is my sample proportion. Again, I'm going to use that to make a forecast, an estimate, an inference, a prediction of what we call P, the population proportion. Some of the older books out there would actually identify this as pi. I think that's the Greek letter for P. And I have mixed emotions about this. I guess I understand and like both of those. SX is my sample standard deviation. And I'm going to use that to forecast my population standard deviation. And this kind of ties into what we call a t-table here. And X bar is a pretty good unbiased estimator for mu. P hat's a pretty good unbiased estimator for P or pi. SX is less of a good unbiased estimator for sigma X, and we need to compensate for that, and that's one of the reasons we use a t-table. As my sample size gets bigger and bigger and bigger, then all of these sample statistics become better and better forecasters or estimators for my population parameters. And I like to say to my students, almost never do we know these numbers. You know, what's the average age of every American right this instant? We don't know that, right? You know, what's the proportion of people in the state of Maine, you know, that drive pickup trucks? We don't know that. So it's very rare that we know these population parameters. And so we almost always have to use sample statistics to make forecasts or predictions for what we call the population parameters. So again, here's my equation for my, well, again, I'll call it the sample least squares regression line. And I showed you that, I think, on my slide. And I want to use these values to come up with what I call the true regression line or the population regression line. This little alpha is I'm going to use that to come up with, this little a, I'm going to use that to come up with what we call alpha. It's a Greek A. And this B here, which is my rate of change or slope, I'm going to use to come up with beta. And I'll continue on with my little chart there. Little a, I'm going to use that to come up with alpha, and little b, I'm going to use that to come up with beta. And so again, on this side here, we have what we call sample statistics. And on this side here, we have what we call population parameters. And we use these sample statistics to make forecast estimates, projections, inferences about the population parameters. I like to tell my students, if it's a Greek letter that you're less familiar with, it's probably a population parameter, mu, sigma, alpha, beta. Of course, this little p here sort of ruins that little pattern for me. And again, some of the older books may actually put pi there. And if you happen to use that in your book, we would accept that on the AP exam. We know what that means, and we're good with that. So when I'm looking at my least squares regression line here, most of us feel that this slope here, this rate of change, is more powerful, more valuable than my initial starting value. Of course, both of them are important with coming up with the equation of my line, but usually a slope or rate of change is considered to be the more important of those two variables. So we have sample statistics. We use those to estimate what we call population parameters. And I'll just go back and show you those two equations. Both of those equations, I believe, are on the formula sheet. This top one definitely is. And so again, don't worry about memorizing the formulas. In one of our review days, Luke and I are going to go know your formula sheet. So we'll talk about all of those formulas and which ones you really need and perhaps which ones you don't. So again, I copied this formula here direct from the formula sheet, all confidence intervals. And hopefully you perhaps been working on confidence intervals with your teachers before we all headed home because of the virus. All confidence intervals are basically built the same way. We start with some sample statistic, and we add and subtract what we call a margin of error. So this margin of error is actually these two numbers multiplied, this critical value times the standard error of the statistic. The standard error of the statistic, different people identify it different ways. This is a little trickier, but when I'm estimating the standard deviation from my data at hand, I call that the standard error. That's going to be dependent upon how big or how small my sample size is. And you probably might have done that when you were doing confidence intervals with either means or proportions. So I'm going to try and write down a couple of formulas that perhaps you've seen before when you were doing confidence intervals. X bar plus or minus critical T, SX over radical N. Again, we call this my sample statistic. I add and subtract those two numbers multiplied are what we call a margin of error. So those two multiplied are a margin of error. This is what we call a critical T value. I'm going to get that from a T table, and that's dependent upon my confidence level and my sample size. And with proportions, what is it? P hat plus or minus square root of P hat 1 minus P hat over N. And that's a critical Z value. Sorry about that. So again, when I multiply those two numbers, I get my margin of error. And sample size is going to be important here in both formulas. It's really square root of N and square root of N on this formula as well. Anytime I'm doing any confidence interval, I want high confidence. So that should make sense. And I want a smaller interval. So I want this high confidence and I want a smaller interval. And one of the ways we do that is by a larger sample size. So a larger sample size is always helpful. I always feel better about the decisions I make. And as a general statement, we tend to get more accurate results with a larger sample size. So this equation down here is newer, and that's, I guess, today's lesson is we want to build a confidence interval using my sample slope, and I want to build an interval that I'm confident captures the true population mean or the population mean of the least squares regression line. And so I guess it's built sort of the same way. I start with some sample statistic, in this case B, that came from my least squares regression line. My critical T value is the same. I get that from a T table, and that's based upon two things: degrees of freedom and my confidence level, and standard error of slope. Well, that parenthesis there, that's a not nice formula. How's that? I'll come back to that in a slide or two. That formula is given to you on the AP Stats exam. I'm going to stick my neck out and say I don't think we would ever ask you to calculate that on an AP Stats exam. It's a little clunky and it's a little cumbersome. Fortunately, technology can do it for us, and many times that's given on the form a generic compute output. Sorry, it's many times included in my generic compute output. So, as a general statement, don't worry about calculating this standard error of the slope. We do expect you to come up with a critical T value, and we do expect you to come up with the sample slope given a generic compute output. Perhaps what's a little different here is my degrees of freedom, which up until now has always been df is n minus 1. Well, degrees of freedom is now n minus 2. So let me see if I can come up with a real quick example here and demystify why it's n minus 2 and not n minus 1. Okay, so earlier in the year when we were using univariate data, one-variate data, I guess up until now, my degrees of freedom has always been n minus 1. And we use that for standard deviation, perhaps first couple weeks of school. It's also part of my correlation coefficient formula. We did degrees of freedom when we did chi-squared, so we use degrees of freedom again. But now we're dealing with bivariate data, so two variable data. And many times in some sort of a scatter plot here, my explanatory variables down here and my response variables up here. And my degrees of freedom is n minus 2. Well, way oversimplifying. Many of my students will say, oh, this is easy, Mr. Murphy. One variable, n minus 1, bivariate data, n minus 2. And that's a nice connection, and that's a true statement. That's not incorrect. But it's a little deeper than that, and I'm probably just going to quickly go over it and oversimplify it a little bit. If I just pick any two data points and graph them on a scatter plot, well, I can draw a line through those two data points, and it would hit both of those two data points, and I guess my correlation would be 1 and my R squared would be 1, but it really doesn't tell us anything. And of course, the sample size of 2 is ridiculously small. I really need a third data point here to come up with some variation in my what we call my least squares regression line. So oversimplifying, that's one of the reasons why we do n minus 2 here, is anytime I have just two data points, I guess I would have a perfect line through those 2 points, and that really doesn't help us. And one of my students will yell out, but Mr. Murphy, the third point could also fall sort of in that pattern and fall directly on the line. And that is a true statement. That's not wrong, but nothing in the real world is ever that nice or that precise. So one of the things that we have to keep in mind is we need degrees of freedom is n minus 2. Again, none of this will be on this year's AP Stats exam, but we want to do a good job of trying to teach it to you, so when you head off to college, you're well prepared. So here's that same formula again, and SEB, standard error of my slope. Well, here's the formula. SEB equals S over SX times square root of n minus 1. And that S on the top is this formula here in the middle. And this SX on the numerator, denominator is right here. And so if you divided this by this times that, you would get this formula, and you can see it's clunky. And yeah, I don't really want to deal with it. And the nice thing is we don't have to deal with it. But I just wanted to show you that those formulas are on your formula sheet for the AP Stats exam. We've never asked students to calculate it, and I'm not sure that we ever would. So don't worry about that, and we're going to go through your formula sheet at one point. So don't worry about it. Similar to all the inference we've done so far this year, we do need to check conditions and list assumptions and whatnot. And so many of the books have this little acronym, I guess. We're dealing with linear models, least squares, regression lines, think liner. I wish I had a good abbreviation for A here, and then it would be exact, but close enough. So L stands for linear. We need to kind of convince ourselves that the relationship between X and Y is linear. The explanatory and response variables are linear. I stands for independent. That hasn't changed. The individual observations are independent of each other. And we check this with our 10% condition, and you're probably, hopefully, real comfortable with that by now. We're looking for some sort of a normal shape for any explanatory variable X. The response variable Y varies according to a normal distribution. And I can check that using maybe a dot plot or a histogram of my residuals. I think Luke did that yesterday. The E stands for equal standard deviations. The standard deviation of Y is the same for all the values of X. And here's our R for random again. The data comes from a random sample of our population or a randomized experiment. So when we're doing these problems, confidence intervals and hypothesis tests, we do need to check for conditions and list any assumptions. And so you want to think about this liner, okay? And you want to think about these 5 things to talk about when you're checking your conditions. And again, if these conditions aren't met, then the results that we get just aren't, they're just not applicable. So here's a t-table. We're probably going to need this to do a couple problems today. Again, this is provided for you on your AP Stats exam. I'm old school, and so I still teach tables. I teach my students how to read these tables. All of this you can get from a calculator. So if your teacher has never taught you how to read a t-table, don't worry about it. I'll show you how to do that on the calculator, but I'll try and do at least one or two problems, maybe using both the t-table and the graphing calculator. So, and I'll tell you why I like the table, but I'm a little old school, and my kids say I'm old fashioned. So I won't tell you my age, but I think I'm older than I look. So here's a classic multiple choice for this concept here, what I call inference for regression. And I'm going to be doing confidence intervals today. Luke's going to be doing hypothesis tests tomorrow. And I know that your exam this year is just free response questions. This is this unit is about 2 to 5%, or let me rephrase that. It would have been about 2 to 5% of a normal AP Stats exam. There just aren't that many free response questions that are related 100% to this topic. So I figured I'd do a couple multiple choice, and I'll try and end up with one free response that hits upon the same concept. So 2002 exam, multiple choice number 21. In a study of the performance of a computer printer, the size in kilobytes and the printing time in seconds for each of 22 small text files were recorded. Okay, again, it's setting the tone. My sample size is 22. And it feels like if my file size is bigger, it's going to take longer to print. I think that's what's happening here, but I'll keep reading and see if I can figure that out. A regression line was a satisfactory description of the relationship between size and printing time. So I guess that was our first condition there, right? We had to check that our data was linear. I could do that by looking at a scatter plot and maybe a residual plot, but we're told that it's reasonable to use a linear model to analyze this data here. The results of the regression analysis are shown below. So again, I would call this a generic computer output here. There's a lot on here, and there's a lot of stuff that we just don't need. So don't get overwhelmed by this. We want to be able to quickly find what we're looking for, use that to answer the question, analyze the data, and move on. What's interesting down here is S equals 0.6174. I think that's the standard deviation of my residuals, but I don't need that for this problem. I think Luke tackled that yesterday. With 22 minus 2 degrees of freedom. Okay, well, there's your little hint that perhaps this is inference for regression, inference for our regression model. And College Board was nice and kind of gave you a little hint here. Again, all year we've done degrees of freedom as n-1, and now all of a sudden it's n-2. Which of the following should be used to compute a 95% confidence interval for the slope of the regression line? Okay, so that's what I was talking about earlier. And I'm just going to go to my document camera and we'll take a look at this problem here. Okay, same problem here. Which of the following should be used to compute a 95% confidence interval for the slope of the regression line? So my confidence level is 95%. My degrees of freedom is n-2 or 20. And again, that was given to us up here. So that was kind of nice. Let's come up with my least squares regression line. Again, all of this data is based upon those 22 data points. So constant coefficient, again, that's going to be my A value. So y hat equals 11.6559 plus the number, the coefficient that goes with the size. I guess that's the size of my file, is 3.478. I probably don't need, I guess I'll put all those decimals down, times x. Again, on a free response question, I would never leave my least squares regression line like that. I would identify both those variables. And since these are English letters and not Greek letters, I'm going to call this my sample least squares regression line based upon, again, those 20 data points. And I want to see if I can come up with an interval that captures the true population slope. So I want to know what that true slope is. If I'm a manufacturer and I know what that true slope is, then I may be able to design my machines a little bit more efficiently. I can make my printer more efficient. And so that's why a manufacturer would want more than just the sample slope here. They want to see if they can come up with the population slope. So I want to use the formula B plus or minus critical T times SEB. Again, we sort of build all confidence intervals the same way. We start with some sample statistic. In this case, it's our sample slope. And I add and subtract what I call a margin of error. These two numbers multiplied give me the margin of error. So we identified the sample slope as 3.47812. So I can eliminate those two answer choices, D and E, pretty quickly. Okay, that would be confusing the initial starting value y-intercept with slope. So that's a common mistake, just watch that. My SEB, my standard error of my slope, is actually right next to my sample slope, SE of coefficient, standard error of coefficient. So that's good to know. That's 0.294. And so if I look up here, I think my answer is A, because that's the only one that has 0.294. But let's see if we can figure out where that this critical T value is coming from. So again, my confidence level is 95%. My degrees of freedom is n minus 2 or 20. So if I go back to my T table here, I'm down at 95%, degrees of freedom over here. And I want to go at the intersection over here of 20 and 95, and I get 2.086. That's that critical T value there. So that's my answer A. And I know they didn't ask me to interpret it, but it's important that we get there. So how would I summarize those numbers? I would say something like we are 95% confident, that the interval 2.86 to 4.09. Again, I think I just did the math, added and subtracted. Captures the slope of the population regression line. Some books call it the true regression line, population regression line, relating the size of the file in my printing time. So again, that's not needed here, but that's important. And Luke and I, when we do some free responses, we'll make sure that you're comfortable sort of summarizing your data. What does that tell us? So I want to go back and show you how to get that critical T value using your calculators. In case you're not as comfortable reading the table, of course, you can get all this from a calculator. I think most of the calculators today now have this feature. If not, you might want to spend some time learning how to read a T table, but let's do second bars. I'll scroll down to inverse T. In many ways, similar to the button right above it, inverse norm. But I'm reading a T table means that I need to worry about degrees of freedom. So we wanted 95% confidence. And so this is an area where we see mistakes on the AP exam. It would be very easy to type in 0.95 here, not 0.975. I'll go back and show you where that comes from. So one of the reasons I'm a table guy is it's easy to sort of type in the wrong number here, I think. But that wants to be 0.975. My degrees of freedom is 20. That was given to us. And again, that's n minus 2. So I'm going to scroll down and gets me back to the home screen. And you can see it's not actually exactly equal to the number that I got from my table, right? I got 2.086, but for rounding errors, that's pretty close, and hopefully you could see that that's the correct answer. So my values are a little bit different, 2.086. The reason that I typed in 0.975 is this were my normal curve here. There's my mean. When I'm doing a 95% confidence interval, I'm hoping that I'm capturing about 95% of my data falls out here in the body of the table. And my lower tail is 2.5, and my upper tail is 2.5 as well. So what I'm really looking for is all of that area right here. And so I add the 2.5 and the 95, or 0.025 and 0.925 to get 0.975. So just watch that when you're using your calculator. The confidence level is not the same as the area. Quick sketch here, and it's easy for me to get there. That's one of the reasons that I actually do like a table. It's pretty easy for me to find 95%. I go up here, I find my degrees of freedom and that intersection point. Now, I'm less likely to make a math mistake, and I do it all the time in the class, and I shouldn't. I shouldn't as an AP stats teacher, and my kids catch me every time and they say, Mr. Murphy, be careful. So just watch that. So let's do at least one more multiple choice here, and I'll take a look at a free response and we'll wind down for this afternoon. So this was from a 2008 practice exam. Raul performed an experiment using 16 wind-up rubber band single propeller airplanes. So I think I have a visual picture. Again, I'm just setting the stage here. He wound up the propeller a different number of times and recorded the amount of time in seconds that the airplane flew for each number of rotations that the propeller was wound. So I think I get what they're asking me to do here. You know, I wind up the elastic band. Probably the more I wind it up, the tighter let it loose, the plane flies longer. But I think that's what's going on. So I call that just setting the stage here. A regression analysis was performed and the partial computer output is given below. So again, I'm going to call this a generic computer output. It's not based upon any one software package. It's generic. It sort of looks like they're giving me the least squares regression line here, at least my sample least squares regression line, y hat equals a plus bx. Sometimes they do, sometimes they don't. I can probably find those two numbers down here. When we go look at the problem, I'll circle those for you. Again, there's many numbers on this output here that we're not going to use. Don't let that bother you at all. Which of the following is a 95% confidence interval for the slope of the regression line? So again, I said earlier that most of us consider the slope the more important of the two variables between my slope here and my y-intercept. That relates the number of rotations the rubber band is wound in the plane's flight time. So let's go do the problem out. Same problem here. So my confidence level is 95%. That feels like a pretty common confidence level, but please understand that there's lots of other ones. I think one of the problems that we may or may not get time to do today had 98%, so maybe we'll go take a look at that. My sample size was what, 16? So my degrees of freedom is 16 minus 2 or 14. So that's important. I need that, and in this problem, I don't see that anywhere up here. So that's important. I need that critical T value associated with this 95% confidence level and those degrees of freedom of 14. Again, my constant coefficient, this number here, well, that's my A value, 0.9241. And the coefficient that goes with the rotation, or the number that goes with the rotation, the number of rotations, 0.04625x. That's going to be my sample slope. Time equals 0.924. Okay, so we got the right equation. I'm going to use this sample slope here to help forecast estimate the population slope, or the true slope of my regression line. So b plus or minus some critical T value times my standard error of slope. Again, when I multiply those two numbers, we call that the margin of error. So my sample slope was what, 0.04625. And again, in a multiple choice scenario, I like to try and eliminate some answers, and this year's test is all free response, but it's always good to eliminate answers, right? Well, the standard error of my slope is usually right next to the slope. So that's this number SEB. I showed you that one slide, and it's no picnic to calculate on a piece of paper or even with my calculator. So, and again, I don't think we would ever ask you to do that. Formula is given to you on the formula sheet, but I don't think we would ever ask you to do that. So my critical t-value for 95% confidence with 14 degrees of freedom. Let's go see if we can find that on my calculator. So second vars, scroll down to inverse t. Again, I don't want to make the mistake of 0.95. Notice they say area, not confidence level. There's a difference. My degrees of freedom, we said was what, 14? I'll go back to my home screen. So it looks like 2.144. 2.144. That's my critical t-value. So let's go see if we can figure out what's the correct answer here. So we had it down to A, C, and E. We did say that my standard error was 0.01565. Well, this one has 0.01. Okay, so I can't eliminate anything there. We did say that my critical t-value based upon 95% confidence and 14 degrees of freedom was 2.144. And so I think the answer is A. And again, I think there's just a rounding issue here that I maybe did, or they rounded a little bit differently. For the sake of time, I won't show you where those two critical t-values, which are incorrect, they're probably coming from something like degrees of freedom of 15 or typing in 0.95 in the area or something like that. So just be careful when you're coming up with that critical t-value. We need the confidence level again, and we need degrees of freedom, and degrees of freedom is n-2. So I'm watching the clock here, and boy, time flies when you're having fun, I guess, as an AP Stats teacher. There's a few more multiple choice that are basically sort of the same thing, coming up with either the margin of error or the actual interval. So they're all similar in some ways. This was an old free response question that had to do with just the sample least squares regression line, correlation coefficient. Maybe I'll try and hit that on Friday when we do nothing but free response. So here's some AP exam practice, and I'll see if I can do this really quickly and get you out of here on time. So John believes that as he increases his walking speed, his pulse rate will increase. That makes sense? The quicker I walk or run, the pulse goes up. He wants to model this relationship. John records his pulse rate in beats per minute while walking at each of 7 different speeds in miles per hour. Looks like we've graphed that. Speed is my explanatory variable. My pulse rate is my response. Again, I wish I had way more than 7 data points, but that's what we have, and we need to make a decision or do an analysis based upon that. I always feel more comfortable with more data in the real world. Scatter plot and regression output are shown below. So keeping conditions in mind, you know, the data does look linear. I might want to do a residual plot. You know, I would do the 10% condition. I would check all of those. Think liner again. Here's my generic computer output. Here's my generic computer output. Again, there's definitely way more numbers and statistics on here than we need. So it's up to us to kind of pick out what we need. I'm going to shift over to my document camera. We'll finish up this problem and I'll wind down for the day. Thanks for staying late if you're still with me. So same problem. Part A, use the regression output, write the equation of the fitted regression line. So again, constant coefficient, there's my A value, speed coefficient, there's my B or my slope. And so down here quickly, I said pulse hat equals 63.457 plus 16.2809 speed. There's my least squares regression line. They didn't ask me to identify the variables, but I would always do that. Do the estimate of slope and intercept parameters have meaningful interpretations in the context of this question? Yeah, I think so. I think so. If my speed was 0, I probably, hopefully still have a pulse, right? So that sort of makes sense. And this sample slope here, I could use to come up with my true slope for my true or population regression line. So yes, again, for the sake of time, both of those seem to make sense. Okay, part C I wanted to do real quick and we'll wind down. John wants to provide a 98% confidence interval. Oh, good. So different number here. I have to think a little bit for the slope parameter in his final report. So I have 7 data points. John wants to come up with a confidence interval that we hope captures the population slope of the least regression line, or true slope. Compute the margin of error that John should use. Assume the conditions for inference are satisfied. So that's the liner there, right? Those are the things that we need to take into consideration. But in this problem, it said, don't worry about it. So the conditions are super important. I don't want to minimize that, but for this problem, we're not going to worry about it. Okay, so I want a 98% confidence, a 98% confidence level, right? So confidence level is 98%. N was 7, so degrees of freedom is 5. So I have what? B plus or minus my critical T value times SEB. When I multiply those two numbers, I get my margin of error. So I need to go get that critical T value. My SEB, well, that feels like it's this 0.8192 up here, right next to my slope. 0.8192. Let's quickly go get my critical T value. Second bars, I'll go down to inverse norm, inverse T. So in this case, I need to think about my area. My confidence level was what? 98. So this probably wants to be 0.99. Okay. Again, I'm adding that lower tail. My degrees of freedom is only 5 here, right? That's small. I would like it bigger. So that's my critical T value, 3.364. And you'll see down the bottom here, I multiplied the 3.364, that's my critical T value, times my standard error of slope, 0.1892. My margin of error is 2.756. So I've gone over here and I'm going to wind down quickly. I apologize for that. Let's just go back to my PowerPoint real quick. If you're still with me, I appreciate it. I hope today was helpful. So we'll post this homework problem on Luke's website for tomorrow. He's going to do hypothesis tests for the true slope. Today I did confidence intervals for the population slope, true slope. Parts A, B, and C, hopefully if you've done least squares regression lines, probably will seem hopefully relatively easy. Part D is where Luke is going tomorrow. So is there statistically significant evidence that electricity produced by the windmill is related to wind velocity? Explain. That's actually a little bit more complicated than it sounds, and that's what Luke's going to do tomorrow. So see what you can do, A through D. Again, I think D will be what Luke covers tomorrow, and it might be a good segue into where he's going tomorrow. So again, thanks for your attention this afternoon. I sincerely hope you're all safe at home and healthy. And that's got to be number one. And so if we all work together and stay positive, we'll hopefully get through this tough time in our country and world's history. The College Board fully understands that all of you may or may not have internet access, and this year's AP Stats exam will be online, probably at home. If you do not have access, please reach out to your administrators, your teachers, someone. The College Board has set up a website below to actually help you. So the College Board's going to do everything in their power to make sure that you do get access to a computer, a tablet, a phone, or something so that you can take this year's AP Stats exam, and that we hope you all take it. So Luke is going to wind down tomorrow with hypothesis test for inference for regression. Friday, I'm going to call what we call Free Response Friday. And that's going to be probably a problem or two on chi-squared, and maybe finish up a problem or two on this what we call inference for regression. So thanks for watching. I think I talked a little bit longer than I hoped. So anyway, I hope you have a great day. Please be safe. And please tune in tomorrow for Luke. Friday, I'll be back for Free Response. And then starting on Monday, we'll do nothing but review for this year's modified AP Stats exam. We'll publish a schedule, and hopefully by next Monday, we'll have a little bit more information about what this year's test format looks like. So have a great afternoon. Appreciate your time, and I hope I helped. Be safe.